Hello, everyone. Good morning, and welcome to Water Reuse Wednesdays. This is the third webinar in our fall webinar series where we're trying to provide useful information about on-site reuse in San Francisco, and we're really excited to have you all today. So what we're going to cover today, hopefully you guys were able to tune in 2 weeks ago or watch the recording of part one of this two-part series on decoding the log reduction targets and pathogen crediting. So in our last webinar, we talked about the log reduction targets, kind of what are they, and then what is pathogen crediting, and went over pathogen crediting examples for membrane filtration and MBR. So if you haven't seen that or you're interested in those topics, I would encourage you can see the recording, it's on our website. So that's available for you. And then today we're going to cover pathogen crediting for some other common treatment processes. So we're going to talk about chlorine and UV. I'll also discuss pathogen crediting without an existing framework for people interested in that. And then at the end, just go over an example treatment train. So just a technical note, if you guys have questions, please feel free to go ahead and put your questions in the Q&A chat, and we will definitely get to those questions at the end. So I just wanted to give a couple reminders of kind of some of the key takeaways from part one 2 weeks ago. So we talked about how the log reduction targets are used to protect public health, kind of the basis for those log reduction targets, and it's all about achieving that target risk goal. So whatever source water you're starting with, it's all about achieving that target risk goal for the end use. Sorry, I'm just gonna close my window right now. So, and then pathogen crediting is actually the way that you demonstrate that you're complying with those log reduction targets. So for an on-site reuse treatment train, you have to achieve total pathogen credit for your treatment train that's greater than the log reduction target. So that's really the key to complying with those LRTs. And in order to do that, each unit process can achieve a specific log reduction value, and that's what we call the pathogen credit. So those were our big kind of conceptual takeaways from last time. So again, how do we do pathogen crediting? So the first step is really addressing this question of picking a unit process that can achieve removal or inactivation of the pathogen that you're interested in, and then looking at how you can prove that removal or inactivation is occurring on an ongoing basis. And that's really the key to pathogen crediting. So I just wanted to reiterate this note here that even though some removal or inactivation can be measured in, a controlled study in a lab or even in a challenge test, that's not automatically equivalent to the amount of credit that you can get, because the credit depends on your ability to demonstrate that you're achieving that removal or inactivation on a continuous ongoing basis using online monitoring. So first we're going to go through pathogen crediting for chlorine disinfection. And this is one that we definitely get a lot of questions on. So in general, chlorine is most effective against bacteria and virus. It can be somewhat effective against Giardia, and it's pretty ineffective for inactivating Cryptosporidium. So in general, when we talk about chlorine disinfection, we're really focused on that bacteria and virus credit, and we generally don't talk about this treatment process as a way to get credit for protozoa reduction. And I'm going to focus on the crediting framework for black water and gray water, which is the Australian water validation protocol. You can Google Australian water valve validation protocol for chlorine, and that document is freely available. And this framework provides a way to get up to 4 logs of virus and bacteria credit. And as we'll talk about in the next slides, that does depend, the amount of credit you can get depends on your operating conditions, your water quality, and what kind of treatment you have upstream. So again, we're not talking about any protozoa credit for chlorine because those cryptosporidium oocysts are very resistant to chlorine disinfection. So the basis for crediting with chlorine disinfection is this concept of CT, which is the product of your chlorine residual and your contact time in a chlorine reactor. So the chlorine residual, that's how much chlorine you have remaining at the end of your contact time. And then the contact time is then the amount of time that your water was in contact with that concentration of chlorine. So it can be a little bit confusing because CT might look like it stands for contact time, but it really is the product of these two things, which is chlorine residual concentration, the C, and contact time, T. And what the water validation protocol does is similar to the EPA CT tables. It links different pathogen log removal values or pathogen credits with a CT value, and it also includes some additional information about water quality criteria, which make this a really good framework for black water and gray water in the on-site reuse scenario. So sorry, this table is really tiny. Don't strain your eyes to look at it, but just to zoom in and give an example here of how it's linking the credit with the water quality conditions. So just say, for example, you knew you were going to have a pH of 7.3, and you're going to have your turbidity is going to be less than 2 NTU, and you also know kind of what temperature you expect to be at. You can use this table to then identify, in this case, you might need to get a CT of 7, for example. So that is the way to use this table. It links your different water quality conditions and tells you what CT you would need to achieve to get a certain amount of pathogen credit. So I just want to go provide a little more information about these two factors that make up the CT. So first it's the chlorine residual. And so just to distinguish what the residual is from what your chlorine dose is. So you're going to dose a certain amount of chlorine to your water, kind of upstream or at the beginning of your chlorine contactor. And then some of that chlorine is going to be consumed. It's going to react with organic and inorganic material that's present in the water. And so your chlorine concentration is going to go down through your chlorine contactor. And what you're going to end up with is the chlorine residual at the end of your contactor. And so that's how much chlorine is remaining after you've already met your chlorine demand. And it's just important to know that the chlorine residual, that's the key thing that goes into the calculation of your CT, but you're going to need to dose more chlorine upstream. So for example, if you were targeting a chlorine residual of 0.5 milligrams per liter, depending on the water quality and how much organics you would expect to be present, you're going to need to dose, maybe 2 milligrams per liter or more chlorine in order to achieve that residual at the end. So then the second part is the contact time. And the contact time, the key thing here is that in the context of calculating your CT, your contact time is basically this. It's your average hydraulic residence time multiplied by this baffling factor. And so what the heck is this baffling factor? This factor basically accounts for, as the slide says, for the hydraulic efficiency of the flow. And basically what that means is, in an ideal contactor, all of the water would move through and spend exactly the same amount of time in the contactor. But in reality, what happens is you end up with a distribution of time that the water spends in the reactor. And so some of the water is going to leave the reactor faster than your average hydraulic residence time. And so the baffling factor accounts for that fact. And so basically different configurations of chlorine contactors will have higher or lower baffling factors, just depending on kind of how wide that distribution is of times that you would expect the water to spend in the reactor. So this is a really important point. If you're calculating CT, you have to have a baffling factor, and that can either be determined through tracer testing, but tracer testing can be expensive and time consuming, so most likely you're going to end up using a default baffling factor. And so this slide is actually just screenshotted from our updated on-site reuse program guidebook. So I encourage you guys, that's a really great resource to take a look at. But basically what this is showing is kind of the default baffling factors that you could expect to use for different types of chlorine contactors. So on the left, what I'm showing is a tank contactor. This is a really simple design, right? It's just a tank where you'd have water coming in and then exiting maybe near the bottom. But what you can see is that the default baffling factor is going to be really low. And that's basically because as soon as you put water in the tank, if it's well mixed, you're going to expect some of that water to basically leave right away. So what does it mean to have a lower default baffling factor? It means that for a given CT, you're probably going to need a larger footprint for this tank. Because what the baffling factor does is it basically reduces your contact time, or makes you need a bigger tank to achieve the same contact time. So that's one option. And then the other option on the right is the pipeline contactor. So the benefit of this is that you can get a higher default baffling factor of 0.6, and that's assuming that you can meet some specific design features that are shown in that footnote. I won't talk about those right now. But the benefit is that you can have a smaller footprint for the same CT. But a pipeline contactor is going to be a little bit more complex of a design. So there are clearly trade-offs with both of these. We know that space is at a premium in on-site reuse, but we also know there's a focus on operational simplicity. So, choosing between these two types of contactors will just be a decision dependent on site-specific factors. Okay, so we know about how to determine our CT with our chlorine residual and contact time. And so how do we translate that to actually doing our online monitoring and proving that we're getting the amount of inactivation that we think we are at all times? So that's where online monitoring comes in. So this is just a little, chlorine contactor that we're showing here, and you're going to be adding chlorine at the beginning. And you need to measure up front. So the flow rate is important because, the flow rate is what determines your contact time. So if you calculated your CT assuming a maximum flow rate of, say, 10 GPM, and then your flow rate went up to 15 GPM, you're no longer going to actually be getting the contact time that you thought you were. So you have to look at your flow rate and make sure that your flow is within the range that you expected. And then also, if you remember back to those CT tables, the turbidity, pH, and temperature were also factors in determining what CT was appropriate. So you also need to verify that you're within the expected range for those parameters. And then at the end, you would be measuring your chlorine residual using an chlorine analyzer. And so with all that information together, you can verify that you are in fact achieving the CT that you thought you were for your specific level of pathogen credit. And just a couple of additional considerations for chlorine disinfection. So pre-treatment and water quality are both really important for chlorine disinfection and making sure you're actually achieving the inactivation that you are anticipating. So one thing that can be really important is the presence of ammonia, which we know is going to be present in black water and likely in gray water as well. And ammonia impacts your ability to do free chlorine disinfection because it reacts with free chlorine and converts to chloramine, which is a less powerful disinfectant. So as a general rule, you should target reducing your ammonia to below 1 milligram per liter in order to do free chlorine disinfection. And then turbidity is another water quality parameter that can impact chlorine disinfection. Turbidity can shield microorganisms from the inactivating effects of chlorine. So if we remember back from that CT table, if you look closely, that crediting framework requires a higher CT as your turbidity goes up. So as you're adding turbidity and having that potential shielding effect, you need to increase either your contact time or your chlorine residual to achieve that higher CT. Okay. So now we're going to get into UV disinfection. This is a topic that we certainly get a lot of questions on. It's very complicated, and I'm going to do my best to try to lay out some key elements of our pathogen crediting framework that we're using in San Francisco. It is a unique framework that we've adapted basically using existing frameworks, but kind of adapting them in a way that makes it appropriate for on-site reuse in our context. So I'm guessing there will be questions. I hope there's questions on this. Please put your questions in the chat box. I'm going to do my best, and I hope that this can address a lot of the questions and confusion that we see about UV. We know this is a really critical process for on-site reuse. So just to start out, talking about UV disinfection and how effective it is at inactivating different types of pathogens. So it is effective against all pathogen types, especially bacteria and protozoa. And then we have this issue of viruses where there's kind of varying effectiveness of disinfection for different types of viruses. So, for example, poliovirus is much more susceptible to UV disinfection than adenovirus. And why am I bringing this up? Why is this important? It's because we know that on-site reuse treatment trains, people are relying on UV in large part, especially to meet their virus log reduction targets. And so when we talk about viruses, right, that encompasses a lot of different types of viruses. So it's important to identify what reference virus we're actually referring to for on-site reuse log reduction targets. So poliovirus, the reason I bring that up is because that is kind of the reference virus for the recycled water context, which we think is more appropriate for on-site non-potable reuse than adenovirus, which is the reference virus for drinking water. So people may have looked at the EPA UV disinfection guidance manual. They have a table of doses that are required to achieve certain virus credits, and that table doesn't match what we're doing in San Francisco. And the reason for that is because that table is based on achieving adenovirus inactivation, and we are focused on more toward the poliovirus because this is a non-potable application. So how do we do crediting for UV? Well, the key is all about UV dose. And this concept is, it has similarities to the chlorine CT framework in that the dose is the product of these two factors, which is the UV intensity. That's really like how much UV light the UV lamp is outputting, times the residence time. So similar to the contact time, right? How much time is the water spending in the presence of this UV light? So there is that kind of similarity, but there are differences that make the approach to UV crediting very different. So UV doesn't produce a measurable residual, right? We can't put, we put a chlorine analyzer on the end of a contactor to measure the chlorine concentration. We can't do that with UV. There's no residual to measure. And then the other thing is that because it's not a chemical disinfectant, it's not getting mixed into the water, right? The water is passing through a reactor and getting exposed to UV light from UV lamps. But because it's not getting mixed in, there's kind of not a uniform exposure to the UV light. So you can end up in practice getting a distribution of doses. So those factors make it a lot more challenging to figure out how much pathogen inactivation you're actually getting in a UV reactor. So the critical part of figuring out the UV dose that you're getting, it's really about how the reactor is validated. So I hope that everybody comes away from this presentation understanding a little bit more about UV reactor validation and kind of why that's so important. And then kind of understanding what parameters are used to confirm dose and how the reactor is operated. Those are the kind of the important factors about understanding the dose and monitoring it on an ongoing basis. So the two validation protocols that we generally use, NSF55 Class A and the EPA UV disinfection guidance manual. So I'm sure you guys have seen those in our materials. So I want to give a little background just to kind of explain the basics behind UV reactor validation, because I think it's important to understand the process, to kind of understand why we harp so much that the validation and the ongoing monitoring is really important for these UV reactors to make sure we're actually getting what we think we're getting. So the way that reactor validation happens is a two-step process. So the first part is basically developing a UV dose response curve. So what happens in this step is that you basically grow an organism and then you expose, maybe it's a petri dish of that organism, to a collimated beam, which is an apparatus that can produce in a controlled environment a known UV dose. So let's say you expose your dish to 20 millijoules per centimeter squared, and then you can actually measure how much log inactivation am I getting, how much of this pathogen am I killing, and you repeat that at different UV doses, and then you can develop what I'm showing here on the right, which is this dose response curve for the particular microorganism that you're using in your testing. So that's the first step, is developing this curve. And then the second step is determining the dose that your reactor is delivering. So this involves basically challenge testing with the same organisms that you just used to develop your dose response curve. So now you can challenge test your reactor with a known concentration of those organisms, and you can measure what's going in and what's coming out. You can measure how much inactivation is occurring. And then you actually back out what the dose was based on how much inactivation was occurring. So basically what I'm showing here on the right, let's say you measured that you had a 2 log reduction through your reactor. You'd come to your dose response curve, you look at 2, you line it up, and you say, okay, that means that I was achieving a dose of 40. So this kind of indirect way of determining what your dose is. And that's why the validation protocol and the organism that's used during validation, that's why those things are so important, because we can't directly measure the dose. So hopefully that made sense. When I first started learning about this, I realized how incredibly complicated it is, but I just want to make sure people kind of understand that this key point about the fact that we can't measure the dose directly. So we really rely on the validation to tell us what the reactors are capable of achieving. And so that's kind of the basics of determining the dose. What you actually do when you validate the UV reactor is you're going to test a range of conditions. So you look at different flow rates, different UV intensity levels, and different UV transmittance of your water. And you use kind of all of those combination of test conditions to define this, what we call this operating envelope. So if we look a little bit closer down at this table, this is just an arbitrary example, but what you can see is that, during this testing, you might develop this data set of, you look at different combinations, so a low flow, high UVT, and your UV intensity measurement, and what dose are we achieving there. You look at these different combinations of conditions. Let's say you were targeting a dose of 40. You can see in your last test condition that when your UVT dropped to 65%, you only achieved a dose of 35. So that kind of creates this cutoff for your operating envelope where you know you can't drop to a UVT of 65%. Otherwise, you're no longer achieving the dose. So the validation testing is really important to establish this kind of combination of conditions under which you can actually achieve the minimum dose that you say you're going to achieve. And then how do we, again, comes back to this question of how do we verify that we're achieving that UV dose on an ongoing basis? The key is measuring the flow rate and the UV intensity. So you have to maintain your flow rate below the maximum rate. That's easy. And then you're measuring this UV intensity. And the UV intensity measurement can account for changes in UVT. So the kind of nice thing about using the UV intensity set point, you just measure the UV intensity, and that accounts for a lot of factors that could affect your dose delivery. So you use that one set point to kind of tell you, are you within your operating envelope or not? And so this is kind of the critical table for understanding what doses can achieve different credits in our program. And this table, again, probably looks different than, you know, other tables in the EPA manual. And remember that the key there is that we're talking about recycled water reference virus rather than drinking water reference virus. So if you know that you need to achieve, you know, 3.5 logs of virus credit, you can come to this table and see that you need to have UV reactors that can achieve a dose of 80 millijoules per centimeter squared. And you can get up to 6 logs of credit for all of these 3 pathogen groups with UV. Okay, so for UV, because this is such a common process and we see a lot of questions about it, I wanted to kind of take it one step further to relate the information that we just talked about with kind of how you would approach putting that information into the engineering report so that DPH, when they review that, can see that you have picked an appropriate reactor, you've provided the information that they need to evaluate if it's appropriate in your treatment train, and if it is going to achieve the credits that you've claimed. So the first kind of parameter here that I've put this blue box around, the UV dose, the value that gets entered here should correspond to how much credit you're seeking, right? So just to scroll back here, if you've put in your pathogen crediting table that you're going to achieve 2 logs of virus credit through UV, then that dose should say 40. And, you know, same for all of these different values. The next one showing here, the influent UVT expected, this is really kind of what do you think the water quality is going to look like entering your UV reactor. So if you have an MBR effluent, this probably shouldn't say 95%. But if you have, you know, if you're talking about a rainwater system, then your UVT expected might be a little bit higher. So this is really, you know, based on your treatment and your water quality, what do you think is going to be going into the UV reactor? And then the minimum validated UVT, that is really, that's the reactor specific minimum validated UVT value, and that is generally provided by the manufacturer, like in the informational brochure, or you could ask the manufacturer for that, because that's something they need to look at during the validation. And I mean, kind of one of the reasons this is included, it's a good check for projects because it doesn't make sense to select a reactor. For example, reactor has only been validated, you know, down to a UVT of 95%, and you're planning to put an MBR effluent with a UVT that's probably going to be more like 75%. It doesn't make sense to use that reactor because it's not going to work. You're going to get an alarm every time. So hopefully projects can use this as kind of a check to see that the reactor they are selecting actually will work in the context of their expected water quality. And then the next one, UV intensity. So this goes back to kind of the importance of that UV intensity set point method. So the UV intensity is that key parameter that is being monitored on an ongoing basis to determine if you're within your operating envelope. And kind of what we've seen as we've learned about the types of reactors that we're seeing in this space is that this information is not necessarily readily available like in the manufacturer's information for all reactors. But for example, for NSF55 reactors, part of that validation, part of them receiving that validation certificate is that they have to set that minimum UV intensity set point value in the reactor. So the manufacturer has to set that, and it can't be changeable. So, you know, the operator can't go in and say, just kidding, I want to change this UV intensity set point, because that set point is what tells you if the reactor is achieving the dose that it says it's achieving. So if that information is not readily available, you can confirm with the manufacturer that they do in fact set that minimum UV sensor reading, which they should do if they have the NSF55 validation certificate. Sometimes that number is available, and if so, it should be put in this table. And then for the validation protocol, so for any given reactor, there's only going to be one applicable validation protocol. So it doesn't actually make sense to say NSF55 and EPA, right? It's going to be one or the other. Some reactors might have both types of validations, but you're going to be identifying the conditions associated with one of those validations, and that information will go in this table. So the validation protocol should really it should either say NSF55 or it should say EPA UV disinfection guidance manual. And then I just want to provide one update, which is that we have this validated, this list of validated UV reactors. This is really just meant as a resource for projects, and it's on our website, and it just got updated today. So there's a new version on our website. I encourage people to take a look at it. The goal was really just to provide projects with more information that's readily available about these reactors that they can then use to select an appropriate reactor, and also to kind of help fill out the engineering report table that I just showed. So this is just a screenshot. There's many more reactors on this list. So I encourage people to take a look. It specifies the validation standard, the associated dose. You can see in the column minimum UV sensor reading where it says manufacturer set. That's kind of what I was talking about, where that number is not always readily available, but it should be set by the manufacturer, and it should be associated with an alarm if it were to drop below that sensor set point. And then you can also find the max flow rate, the minimum UVT, and the potential pathogen credit that's associated with that dose. And just to remind people, this is an informational resource. This is information that's readily available. It's just compiled for your convenience in one place. Projects, still need to do their due diligence if they're selecting reactors to make sure that that reactor is appropriate for their water quality and can be integrated with their control system, that they could initiate, automatic shutdown or diversion if an alarm was triggered. So there's a variety of factors that projects still need to do their homework to make sure that the reactors are appropriate. But I do encourage you to look at that updated list. And our website URL is on the last slide, just so we'll get there. Okay, so that was UV. So I do want to talk a little bit about pathogen crediting without an existing framework. This is something that we get questions about, and it is possible for projects to get credit for unit process without one of the existing frameworks that we've talked about. But one of the things that we tell people is that it is likely to require a significant level of effort This is kind of one of the main reasons why we rely on existing crediting frameworks in the first place, because it just streamlines the process. We're relying on, information that's already been compiled. Lots of effort has already gone in there, so it makes it easier for everybody. But if you're interested in getting credit for a process, it is possible. It will require significant microbial challenge testing that ultimately may end up being more expensive than the cost of the technology itself. That will depend on, what the technology is. But if you're interested in this, what will be required is an extensive set of challenge tests with representative microorganisms, so that you can, first of all, quantify the pathogen reduction through the process. That's kind of the first thing. That will be using actual pathogens or potentially appropriate microbial indicators. But then there's this other part, which is measuring surrogate parameters, and those would be used to link your measured pathogen reduction with something that you could measure online continuously, right? Because we know we can't measure viruses online continuously. So you might, instead measure turbidity and look at, is there a correlation between pathogen reduction and turbidity reduction, for example. And you would have to consider a range of water quality. So you have to understand how changes in water quality would affect your pathogen reduction and also your surrogate reduction, right? Because those things have to be correlated. And then from all of that testing and data analysis, you could develop your water quality and operating requirements that you would use to demonstrate your ongoing pathogen removal performance. And just to give you guys a sense of kind of, what might be the cost of this type of work, if you're going to actually do challenge testing using virus, this can be really expensive. It can cost, more than $1,000 per sample. And so when you have to do challenge testing that looks at a range of operating conditions, that could end up being 20 paired samples. So, you might be looking at many tens of thousands of dollars to validate one treatment process. So I just want, people to understand that this can be done and it will require significant investment. You'd have to coordinate with DPH about your test plan and your data analysis and kind of understanding the conclusions. So that is an option. So to kind of summarize this discussion of pathogen crediting, I know I just threw a lot of information at you guys, but pathogen credits in general can be assigned via either existing crediting frameworks, we talked a lot about those, or as I just mentioned, developing and conducting site-specific validation. So both of those options are available. But utilizing existing frameworks is streamlined and efficient. It's probably the easiest way to comply with the LRTs. And it's all based on using online monitoring that allows for continuous verification and pathogen reduction. It's really the key for public health protection. So I am just going to show actually just one example treatment train to kind of tie these things together. And this is also a screenshot from our guidebook. So our guidebook has more example treatment trains. Again, I encourage you to check that out. We've revamped these treatment trains to try to include more detail and make them more useful. So this is an example treatment train for gray water. And kind of the workhorses for this treatment train in terms of getting pathogen credit are the MBR and the UV. So the key for the MBR, as we talked about last week, is really being within that tier 1 operating envelope. So if you monitor those tier 1 parameters online, that includes a lot of parameters in the MBR and then also the effluent turbidity, then you can achieve those default MBR credits that are shown, sorry, it's kind of small text below that reactor. So with those credits, for the UV disinfection, that's going to get the remainder of the credits. And again, the keys there are measuring your flow rate and your UV intensity, in this case, to verify your dose of 120 millijoules per centimeter squared. So those are the treatment processes that together would be achieving the LRTs. And then, you know, we haven't covered in these kind of the other water quality requirements, but this train does show you'd need, you know, a place to sample your BOD, TSS, and total coliform to make sure you comply with those other water quality requirements. Those are also important. We're also showing this three-way valve, which would basically be a mechanism if you had off-spec water. Let's say your UV intensity dropped below the set point, you'd need to trigger, you know, potentially would trigger an automatic diversion so that you start sending that water to sewer and instead of sending off-spec water to the building. So that's the first part of the treatment train. I had to break this up into two because it's a very widespread. So then what I'm showing on the end here, this is the continuation after that three-way valve. So this is the treated water storage tank where the water is getting chlorinated, and this is not for pathogen credit. It's really just for secondary disinfection to maintain a chlorine residual in your distribution system, which is also very important. And you have, you know, your potable makeup water connecting here via an air gap as your backup supply. So I know there's a lot of information in there and I went through those quickly, but again, I encourage you to take a look at our guidebook and there's additional resources in there. So that is the end. I put my email address on here. You can always feel free to email me with questions. And then also that's the URL for our website where you can find links to all of our resources, including that updated guidebook and including that updated validated UV list. So I think it's time to take any of your questions.
Hey everybody, this is Taylor Chang with SFPUC. I work with Sarah on the on-site water reuse program. Nice to see so many people on the webinar today. And I will be queuing up some questions for Sarah. We've got a couple. While I'm pulling that up, Sarah, do you want to give folks an update on our calculator?
Yes, I do. So we had talked, I think, on our first webinar about how we have been making some updates to our water use calculator. That's kind of the key resource that people use to estimate their planning level estimates of on-site supplies and demands. And that update has been completed. And you can also find that new version of the calculator on our website. There's a single site and a district scale version of that calculator.
Great. And as I'm reading off these questions, please post your questions in the Q&A and we will get to them as they come up. So one question was, can you provide a link to the guidebook you mentioned as well as one for the Australian standards or LRTs that you are using? So the guidebook, link to the guidebook we provided, but maybe if you could expand on the reference to the Australian standards and where folks can find the LRTs.
Yeah, so let's see, what's going to be the easiest way for me to tell people how to find that? Truly, I think if you just were to Google Australian water valve fluorine disinfection protocol, it would be the first thing to come up. I'm not sure that we have linked to it on our website. It's also, I believe it's referenced in the guidance manual that was recently published. Taylor, maybe you can post a link to that, to the guidance manual in the chat, which has a lot more information about pathogen crediting and I believe has references to all of the frameworks that are mentioned.
Yes, I will post a link to the guidance manual.
Okay.
Another question. Can you please point us to a reference relied upon for the basis of the 0.6 baffling factor requirements for the plug flow contact or utilizing the assumed turbulent and L/D conditions?
Yes, that is a great question. The answer is I can't point you to an existing source for that. That Default baffling factor we developed with assistance and data from our consultant. So if you want more information about how we came to that number, please go ahead and email me and I can provide more information about that, but it's not published in like an existing guidance manual type of document.
Okay. Second question. Has anyone successfully proposed disinfection credits for an MBR using the water valve requirements in San Francisco?
Yeah, good question. I believe we have not seen people proposing to comply with the Tier 1 and get MBR credits. And I think that's just because people are, rather than continuously monitoring all of those online parameters, people are opting more toward using UV to get all or most of the credit. It's not to say we won't see it, but I don't believe we have actually seen a proposal for the Australian water valve MBR credits.
Great. Not seeing any other questions yet, but as folks are typing that in, maybe you can give us a sneak preview on what we're going to be presenting on the last webinar of our fall webinar series.
Yes, so our last webinar is 2 weeks from today at the same time, and it's going to be a lessons learned webinar. So you won't have to listen to me and Taylor. You'll get to hear from some guest speakers, people who are involved in design and installation and operation of on-site systems in San Francisco. And they'll be sharing as much as they can about their experiences and their lessons learned navigating our system. So we hope you guys can all make it for that one too.
Awesome. Well, I am not seeing any other questions. So great job. And I will turn it back to you for any final remarks before we end today's session.
No, I think that's all I have. I'm really glad you guys, thanks for making the time to join us. And just again, always please feel free to reach out with any questions that you have as they come up.
Thanks, everybody. Take care.